The Ultimate ACSL Contest 1 Review Guide. This covers all the materials that will appear on your ACSL multiple choice, whether you're in the senior, intermediate, or junior division. This is part of the Road to ACSL Gold playlist, which is going to discover and share all of the topics covered on the 4 different ACSL contests throughout the season, along with a finals review guide, which will cover all the material in one 30-minute video. So this is your road to getting a perfect score on the ACSL multiple choice and getting a gold in the finals, so let's get started. The first topic covered in ACSL Contest 1 is computer number systems. So computer number systems are different ways of storing numbers that are used by computers. So humans usually use the decimal system for storing different values, which is each column represents a specified power of 10. However, the binary, octal, and hexadecimal systems are all tested on ACSL, and they use powers of 2, 8, and 16 to store these values. So notice how it is impossible for the binary system to store a value larger than 2 in its columns. It only stores up to 2, because otherwise its columns would simply be shifted. For example, 2 to the 0 is 1. If we had 2 of those, then that would mean that that's equivalent to 1 of 2 to the 1, which is why those values just are impossible to be stored in these systems. So you'll notice how, because binary has such little numbers, 2 to the first, 2 to the second, etc., a binary number will become very long when the number increases in its size compared to an octal, decimal, or hexadecimal value, which are not going to grow in such a large amount. It takes a lot more digits and values to store binary numbers. This was largely part of the reason why the binary system isn't really used by humans or programmers, and it is largely used by computers, because this makes it easier for them to compute things, but it makes it longer and more difficult for a human to be able to compute using these values. But they're still very useful to know for ACSL. So the octal system stores numbers in powers of 8, which means that it can store digits 0 through 7 in each column, and it grows through powers of 8. So this first column is going to be 8 to the 0, which is 1s, then this is 8s and 64s. So the way that these number systems are used in ACSL, they will typically require a conversion. So when you're converting, it is it's recommended for beginners to use decimal as an intermediary when converting between 2 different methods. So take, for example, trying to convert octal to binary. So first, you would start by writing out your table. So 431 in octal is equal to 4 times 8 squared plus 3 times 8 plus 1 times 1 in decimal. So this isn't going to give you your results in the other number system. This is the way to convert from any system to its decimal value. So this is what the value is equal to in decimal, 281. So next we would take 281 and convert it to binary. So to convert something from decimal to binary or vice versa, you need to know your powers of 2. So the largest power of 2 that can fit into 281 is 2 to the 8th, which is 256. So you would subtract that value from your initial number, and you'd get 25. So you would keep on repeating this process, continuously taking away the largest powers of 2 as you can until you get to 0. And there's never going to be a case where your final result is not 0. And if you cannot get to 0, that means that you have made a mistake somewhere else in your process. So the decimal system here in your little tip acts as a good intermediary when converting between these systems. So let's visualize this binary value as what it is. So here we have 2 to the 8th. We're going to place a 1 here because we subtracted that. The next value that we subtracted was 2 to the 4th, so a 1 goes into this column. However, we did not touch these values at all. 2 to the 7 through 2 to the 5, they were not used in our conversion, which is why a 0 is placed there. 2 to the 3rd and 2 to the 0th are also used, which is why those columns will have a 1. So that is that value. 431 in octal is equal to 1000110001 in binary. Next, ACSL requires competitors to know the operations between different number systems. So take, for instance, addition, division, subtraction, and multiplication. So the most simple way to go about these problems is to convert all the different operands into decimal. You can add, subtract, multiply, or divide using regular operations, and then you can convert your result back into the required computer number system. So take, for instance, if we were adding 431 in octal plus 100 11001 in decimal, and we wanted our result back in hexadecimal. So we would essentially convert 431 to its decimal value. We would add those two together and then convert our result back to hexadecimal if that's what ACSL wanted the results in, and then that would allow for us to get our final result back. And this is a lot easier to do simply because these different operations have different rules when you're treating them and using different number systems. So it is most simple to learn your operations, practice them in decimal systems, and then convert your final answer back to the required number system on ACSL. The next topic that's going to be covered on ACSL Contest 1 is recursion. So recursion is when a function repeatedly calls itself to get a final result. So in ACSL, there's never an issue called infinite recursion, which means that a function will endlessly keep calling itself. You will always get a result back when you're tracing a recursive function. This is very important. So let's go through this first example to see how that works. So here it asks to find f of 17. So we're going to start with our upmost condition, which is if x is greater than 10. In this case, x is greater than 10, which means that the function is going to satisfy that condition, and we can set it equal to f of x minus 2 plus 8, which is, in this case, f of 15 plus 8. So next, we don't know what f of 15 is, so we need to solve for that too. So f of 15 is also greater than 10 because x is greater than 10, so that condition is true, which means that it's equal to f of 13 plus 8. So essentially, we keep on working down this pathway until we get to f of 11, which is equal to f of x minus 2 plus 8. So that is equal to f of 9 plus 8. And now when we're looking at f of 9, x is not greater than 10, and it's also not equal to 10. So this condition does not fit. X is less than 10, which means it's returning a finite value, which is, in this case, 9 plus 8, which is 17. So next, we can plug that 17 into our different expressions. So f of 11 equals to f of 9 plus 8, which is 17 plus 8, which is 25. So now we're plugging in 25 into this value for f of 11. So we keep on working our way upwards until we get to f of 17, which is equal to 49 as our final answer. Next, we can solve for f of 9. So using our past logic and our tracing, we know f of 9 is equal to 17. This is never going to change no matter how many times you retrace a recursive function. You should always get the same output. So we can use f of 9 is equal to 17 and substitute that for f of 9 in this equation. So now we know f of 9 is equal to f of 17. Now, from our past tracing, we know f of 17 is equal to 49. So this means that f of 9 is equal to 49. And sometimes ACSL is going to have several nested functions, which are recursive. For instance, I've seen it go up to 5 different nested f of x's, and what you would do is you start with the innermost one, you solve for that result, and you work your way outwards until you get your final answer. And a lot of the times you can reuse different values that you have, so like we were able to reuse f of 9 equals 17, and we didn't have to retrace the function all the way. So always try to take as many shortcuts as possible when you're tracing these functions, because typically that is what is expected of you. So next, sometimes recursion can have 2 different parameters. So this makes it a little bit more difficult, so we can see how that works here. So we here notice that f of 1235 fits 2 conditions, x is greater than 10 and y is also greater than or equal to 30. However, because we're working on this top to bottom, we always start with the topmost condition, that is the one with the most priority. So because x is greater than 10, we are going to be using that condition when evaluating the function. We get that is equal to f of 530 times 2 plus 8. Next, f of 530. That doesn't fit the first condition up there, but it does fit that y is greater than or equal to 30, and notice how this is equal to f of y minus 4, x plus 1. So they are actually swapping the x and y parameters in this method. This is very important because it is very common for ACSL to try to trick competitors and swap these parameters. If you don't notice that this is not x minus 4y plus 1, but it's y minus 4x plus 1, then you can get tricked, you can mess up your tracing, and you can get stuck in a loop of either infinite recursion or you can get a wrong answer. So let's keep working through this problem. So if you keep on working through it correctly and swap those parameters, you essentially make your way down to f of 5, negative 9. So this fits only the very last condition, which then makes it equal to x times y over x plus y. So then we get our answer, negative 45 over 4. So we continue by plugging in this value into our functions and adding 8 as needed, and then we finally make our way up to negative 314, which is equal to f of 1235. The next kind of problem that you're going to have is, what does this program do? So note that usually these will be a lot more complex than the example that I have here. However, I'm mainly focusing on showing you all how to trace this problem rather than how to work with the more complex ones, because truly the more complex ones aren't as intimidating if you know how to solve them correctly, and the length or the complexity of the problem in that end ends up not making a difference. So I usually use a pen and paper, and you're going to make a table to store all the variables that are used in your problem. It's going to be usually up to 6 is the max I've seen with ACSL contests, but usually 4 to 5 is what you're going to be required to trace. So here I have A, B, and C. Their initial values are 7, 4, and -2. Step is the iteration of our problem. So 0 here is before the program even ran the 0th iteration. Those are the initial values of our variables. Now in the first iteration, it's saying, well, A is greater than 0. That does check the condition. So we're adding C to B. So C is negative, so B ends up being 2. Then C is equal to A mod 3, which is in this case equal to 7 mod 3, which is 1. And then we're taking away 2 from A, which is 5. And then we're checking if B mod C is equal to 1. Now, B is equal to 2, C is equal to 1. 2 modulo 1 is 0, it's not 1. So the while loop continues. So we're going to keep on going. B plus equals C, so 2 plus 1 becomes 3. C is equal to A mod 3. A in this case is 5, mod 3 is 2. So C is now equal to 2. Next, taking away 2 from A, so A minus equals 2, that's equal to 5 minus 2, which is 3. Now, if B mod C is equal to 1, 3 mod 2 is equal to 1, so that means the while loop is ending. So these are our final values for A, B, and C. So now we're printing them, A plus B over C, 3 plus 3 over 2. So in ACSL, you will be using integer division, which means if you're dividing an integer by another integer, the decimal value will be truncated. Notice there's no rounding, it is simply truncated. So 3 over 2 is 1.5. We are not rounding that to 2, we are truncating the decimal, so it becomes 1. 3 plus 1 is now equal to 4, so at the end of the program, it will print 4 as its final value. So that's all that I have for ACSL Contest 1. I highly recommend looking at the ACSL official Wikipedia page for any past contest problems, and there's also a myriad of additional resources that you can check out of similar caliber. Thank you for watching.